This is Dirichelet test of convergence of improper integration, right? And this is the Dirichelet test of type 2. What is the test of type 2? Here the range of the integration is not infinity. Here in the lower range, that is at x equal to a, the function has infinite discontinuity. Okay, now the statement of this test is, let fx be bounded and monotonic and fx tends to 0 as x tends to a plus or a plus 0. Also gx be bounded and integrable in a plus epsilon to b, where epsilon is greater than 0 and less than b minus a. Okay, here we exclude the point a because gx has infinite discontinuity at x equal to a. Having infinite discontinuity at x equal to a and integration a plus eta to b gx dx is also bounded for 0 less eta less b minus a, then Dirichelet test state that integration a to b fx gx dx is convergent, right? To prove this theorem, we use here two important theorems of integral calculus. The first one is second mean value theorem of integral calculus in Oester's form, and the statement of this is, if fx is monotonic in AB and gx is bounded and integrable in AB, then for xi which is lies between a and b, integration a to b fx gx dx, this is equal to fa into a to xi gx dx plus f of b into xi to b gx dx. This is the statement of second mean value theorem. And the second theorem, this is a theorem of improper integration also. This is Cauchy's criterion. Cauchy's criterion is integration a to b fx dx, where fx having point of infinite discontinuity at x equal to a, like this problem. Then if for any epsilon dash greater than 0, there exists delta greater than 0, where delta, the value of delta depend on epsilon dash, such that mod of integration a plus epsilon 1 to a plus epsilon 2 fx dx less than epsilon dash for 0 less than epsilon 1 less than epsilon 2 less than delta, then the integration a to b fx dx is convergent. These two theorem we use here. Okay, we already write two statement. Now here we first write or first use second mean value theorem of integral calculus, because fx is monotonic, also here fx is monotonic and bounded, right? And gx is bounded and integrable. Also it is given that gx is bounded and integrable. So we use the second mean value theorem of integral calculus and get integration a plus epsilon 1 to a plus epsilon 2 fx gx dx. This is equal to f of a plus epsilon 1 into integration a plus epsilon 1 to a plus epsilon dash gx dx plus f of a plus epsilon 2, the upper range, into integration a plus epsilon dash to a plus epsilon 2 gx dx, where 0 less equal to epsilon 1 less equal to epsilon dash less equal to epsilon 2 less equal to b minus a. Also it is given that this integration is bounded. Okay, so we can write there exists m greater than 0 such that for all eta belongs to 0 to b minus a, mod of integration a plus eta to b gx dx less than m. Right? This is from the condition given. Now we start with this integration, that is integration a plus epsilon 1 to a plus epsilon dash gx dx. This integration can be written as integration a plus epsilon 1 to b gx dx minus integration a plus epsilon dash to b gx dx, right? Because here this is a plus epsilon 1, this is a plus epsilon dash, this is a plus epsilon 2, and this is b, and this is a. We first take integration a plus epsilon 1 to b, this integration, and then subtract the integration from this to this. So there remains this integration. So we get the result as same on the left side. Now we use the property of modulus and get less equal to integration a plus epsilon 1 to b gx dx mod plus integration a plus epsilon dash to b gx dx mod, and these two integration must be less than m if eta less than this, and we get less than 2m because or since here eta, here epsilon 1 and epsilon 2 lies between, because or since epsilon 1 comma epsilon dash belongs to 0 to b minus a, right? We get this is less than 2m. Now in similar manner we also get this integration a plus epsilon dash to a plus epsilon 2 gx dx also less than 2m, right? And we name this relation as 1, this relation as 2, and this relation as 3. Here it is given that fx tends to 0 as x tends to a plus 0. That is given that limit x tends to a plus fx, this is equal to 0. And from the definition of this limit, we say that for any epsilon greater than 0, there exists delta greater than 0 such that delta is dependent on epsilon, with mod of f of x less than epsilon by 4m for all a less than x less than a plus delta, because here the range is a to b, so we cannot move the left side of a, so we take only a to a plus delta. Okay, and using this definition we can write easily mod of f of a plus epsilon 1 less than epsilon by 4m and mod of f of a plus epsilon 2 less than epsilon by 4m, okay, for all a plus epsilon 1 less than a plus delta less than a, also a plus epsilon 2 less than a plus delta less than a, or we can write 0 less than epsilon 1 less equal to epsilon 2 less than delta. Okay, now from 1 use the relation to 3 and we name this relation as 4. We get, by taking modulus on both sides of 1, we get mod of integration a plus epsilon 1 to a plus epsilon 2 fx gx dx less equal to mod of f of a plus epsilon 1 into mod of integration a plus epsilon 1 to a plus epsilon dash gx dx plus mod of f of a plus epsilon 2 into mod of integration a plus epsilon dash to a plus epsilon 2 gx dx. We put all the value and get, this is epsilon by 4m, this is 2m plus epsilon by 4m, this is 2m. So this is less than epsilon, because here epsilon by 2 and here also epsilon by 2 less than epsilon. Now we use the Cauchy's criterion of convergence. We already say here, if a plus epsilon 1 to a plus epsilon 2 fx dx less than epsilon dash, okay, then it is convergent, and we get the same condition, but here epsilon dash and here we get epsilon. These two are same result. Okay, so we say that by Cauchy's criterion, so by Cauchy's criterion of convergence, we say that integration a to b fx gx dx is convergent. Okay, this complete the proof of Dirichelet test of type 2. Here we take two problems to see the application of this theorem, and the first problem is integration 0 to 1 by x to the power 3 by 2 into sine 1 by x dx, and the second one is integration 0 to 1 by x square into cos 1 by x square dx. Okay, these two applications are also very important for your exam. Now here we first see that the range of the integration are finite, like this theorem. Okay, and we write this integration as integration 0 to 1 x sine 1 by x into 1 by x to the power 5 by 2, right, dx, and we take this part as fx and this part as gx. Okay, now it is clear that limit x tends to a plus 0, that is here 0 plus 0, because the lower limit a, this is equal to 0. Fx, this is equal to limit x tends to 0 plus x sine 1 by x. Clearly we know that this integration is 0. Okay, and gx, this is equal to 1 by x to the power 5 by 2, has infinite discontinuity at x equal to a, this is equal to 0, that is at the lower range. Also integration 0 plus eta to 1 by x to the power 5 by 2 dx, this is equal to x to the power minus 5 by 2 plus 1 by minus 5 by 2 plus 1. Range is eta to 1, and this is given by minus 2 by 3 into 1 by x to the power 2 by 3, 3 by 2. This is 3 by 2 eta to 1. So this is equal to minus 2 by 3 into 1 minus 1 by eta to the power 3 by 4, where eta greater than 0 but less than 1. Clearly this is also bounded. Hence the first condition and the second condition satisfied. So using Dirichelet theorem, we say that this integration is convergent. Right? This is an important application of this theorem. And similarly, like this, we apply Dirichelet theorem for this problem. Okay, we may multiply here x and here also x, or we may be multiplied by x square with numerator and denominator, then we get this. Okay, sorry, this is x to the power 4. This is the today's class. Thank you for watching.